Good afternoon. Welcome to the 21st annual Victor Paul Starr Memorial Lecture. As you know, we have had these lectures for over 2 decades in this department in honor of Victor Starr, who was a faculty in our department. Actually, was the Department of Meteorology when he was there. And these lectures are on broad-ranging topics in atmospheric sciences. So we're very pleased to have today the first such lecture in atmospheric chemistry. And we're particularly pleased that it's Professor Paul Crutzen who's giving the presentation today. Paul is a close colleague and friend of mine, and I think it's very fitting that he will give us this first atmospheric chemistry lecture, because Paul is really, or started as a meteorologist, but eventually he saw the light and became a chemist as well. So let me tell you a few things about Paul. He was born in Amsterdam, in the Netherlands, and what he studied first, I believe, was civil engineering in Amsterdam. In fact, his first jobs were as an engineer, in the bridge construction bureau of the city of Amsterdam. Then eventually he moved to Sweden, and where he was working at the house construction bureau. But eventually he got a PhD in meteorology at the University of Stockholm in Sweden. I think he started there with a job as a computer programmer, but switched to meteorology, of course. In 1974, between 1974 and 1980, he came to the United States, where he was the director of the Air Quality Division at NCAR. I think we call it the Atmospheric Chemistry Division now, at the National Center for Atmospheric Research. And in 1980, he went back to Europe, to Germany, where he has been there until now, as a director of the Atmospheric Chemistry Division of the Max Planck Institute für Chemie in Mainz. At the same time, he has been and is still a part-time professor at the Scripps Institution of Oceanography in San Diego, as well as in Utrecht University in the Netherlands. Now, Paul has many honors and awards, several pages, which I won't take the time to read, but I thought I'd select just a handful with a certain bias, as you'll see. One of them is he is an AGU fellow. He became a fellow of the American Geophysical Union in 1986. I just became a fellow myself just a year or two ago. In 1989, he got the Tyler Prize for the Environment. Happens to be a prize I also received at some point in time. Another very interesting prize is the recipient of the Max Planck Forschungspreis, which is a program that is given to a German investigator in collaboration to an American scientist. So I was fortunate to receive that with Paul. In fact, it was a very productive prize because we got funding to do research, and we have a wonderful student, Thomas Koop, who was a Paul student to begin with and became my student afterwards. And then in 1995, Paul received the Nobel Prize in Chemistry, and of course I had the honor of sharing it with him and with Sherry Rowland. So these are the only prizes I will mention. But let me do one additional thing. I want to read you the title of his PhD thesis in 1968 that he got at the University of Stockholm. And it is the determination of parameters appearing in the dry and the wet photochemical theories of ozone in the stratosphere. So that was in 1968. So this really brings me to explain to you that Paul did this groundbreaking work in understanding how the stratosphere functions, how the chemistry of the stratosphere works, really discovering the catalytic cycles. The nature of these cycles is very important in explaining how is it that trace species, in this case nitrogen oxides or hydrogen oxides, very small amounts of certain catalysts can have this very large effect in controlling the abundance of ozone in the stratosphere. And also in Stockholm, the Paul had a second thesis, I think it's a doctorate in science thesis, this was in 1973, and the title is On the Photochemistry of Ozone in the Stratosphere and Troposphere and Pollution of the Stratosphere by High-Flying Aircraft. So this is another milestone. Paul was really the first one to recognize that human activities could impact ozone in the stratosphere, which is this major natural system, that it's truly a global issue. So that all goes back to his early days in Sweden. Since then, he has made numerous contributions, both to stratospheric chemistry as well as to tropospheric chemistry. Again, too many for me to list. But he will talk to us today about tropospheric chemistry. The title of his presentation is The Major Role of the Tropics in Atmospheric Chemistry, the Need for Strong Research Efforts. I'll give you Paul Crutzen.
Well, thank you for this introduction. Now, you took 10 minutes of my talk. So I have to shorten it down, I guess, because everybody wants to go to the drinks afterwards. Good. Well, it's nice to be here, and in fact, to have such an audience so late in the evening, because normally this time I go to bed. Well, here we have, my lecture will not be really for the experts. So the experts who, this will be a little bit of a fundamental lecture on how the chemistry of the atmosphere works. So if the experts already know that and they know it, they can leave, but you're also allowed to stay. If we look at the distribution of ozone in the atmosphere, and we all know that there's almost everything is in the stratosphere. And about the stratosphere, I will not speak very much in this lecture. There's very little ozone in the troposphere. At most, about 10% of all atmospheric ozone is located in the troposphere. And for a long time, it was thought that that ozone was not very interesting. Some meteorologists had been looking at it. It was normally believed that ozone would come down from the stratosphere into the troposphere and would be destroyed at the Earth's surface. This was basically the belief, say, around 1970. Well, this, and it, in fact, ozone is, of course, coming down from the stratosphere and the troposphere. This is the picture which was prevalent in the early days. The ozone was produced in the stratosphere, and a very small fraction of it, actually, if the flux of ozone from the stratosphere into the troposphere is less than 1% of all ozone formed in the stratosphere. So a little small leakage will bring ozone into the troposphere, but it was believed for a very long time that that was the whole story, that it was then destroyed at the ground. And that this happens is also sometimes very clearly observed. Here we have a so-called intrusion of material from the stratosphere into the troposphere. We see here isolines of radioactive species, which in the 50s was produced copiously in the stratosphere by bomb testing. We see ozone, and we see something meteorologically stable or almost inert capacity, namely the potential vorticity. And you see all these isolines going into the troposphere, and part of this ozone which follows that is then also staying in the troposphere. So the picture looked extremely clear. And in fact, very little interest was devoted to ozone in the troposphere until roughly the middle of the 70s. We all know how important ozone is. The stratospheric ozone filters out basically all radiation between 240 and 300 nanometer from, which is coming down on the Earth from the sun. However, this filtering is not perfect. Around 300 nanometer UV radiation comes down to the Earth's surface, very much dependent on the amount of ozone in the stratosphere. And this radiation is harmful. Too much of it, we all know it in summertime, sunburns, too much of it is not very good for you. So that is, normally the UV radiation is considered to be a negative factor. Also, ozone in the troposphere is considered to be negative. It harms people, lungs, and the lungs can be damaged and so on. So, and plant life can be damaged by too much ozone in the troposphere. However, it turns out that this ozone in the troposphere has also very important, let's call it positive consequences. And one of the reasons is that, and it goes back to some simple reactions here, ozone photolysis at wavelength below, nowadays we say almost 400 nanometers, below, in this wavelength region, produces O atoms in an electronically excited state, O single D, which then has enough energy to react with water vapor to make hydroxyl radicals. And these hydroxyl radicals, which play an enormously important role in keeping the atmosphere clean, because the hydroxyl radicals react with almost all species which are produced by nature or by mankind and deposited in the atmosphere. So here we summarize the two reactions again. By the way, you see here that because of these two reactions, ozone is destroyed. We come back to that, to the budget of ozone in the troposphere. And we see here a number of species which react with OH, like methane. Methane reacts rather slowly with the hydroxyl radical. And it has a lifetime on average around the world of about 8 years. And that means that methane is found both in the northern and in the southern hemisphere, although almost all ozone, all methane is produced in the northern hemisphere. So, but we go to other species like ethane, reacts much faster with OH, and we see definitely much more in the northern hemisphere than in the southern hemisphere. We go to propane, lifetime of a few years, or a few days, 10 days, and we hardly find anything of that in the southern hemisphere. And of course, isoprene, which is emitted by deciduous forest, has such a short lifetime, orders of hours, that we only find this compound close to the forest regions. We have a number of sulfur, chlorine, and many other gases which are removed from the atmosphere by reaction with OH. And this was a major discovery which goes back to 1971 by Chip Levy, who worked then here at the Smithsonian Institute just down the river almost. Before this paper, before this knowledge, it was simply not known how compounds which go into the atmosphere, how they are removed. And I show you later some funny estimates about budgets of trace gases which were produced at that time, before that time, because they were far out from reality. Now, in the lowest figures, the lowest two figures here, I sort of summarize the good and the bad of UV radiation. Here we have the positive factor. If we multiply the efficiency with which O single D atoms are produced by ultraviolet radiation, multiply that with the flux of ultraviolet radiation down to the Earth's surface, which is a strong function of ozone going down to a shorter wavelength, we get curves which look like this, dependent on the amount of ozone in the stratosphere. That's the positive part. But if you look at the DNA damage, we get a curve which looks very similar. So you cannot say that UV radiation is only damaging. it has positive, it has negative sides. In the 70s, it was also realized that ozone in the troposphere was not inert. Of course, we saw already one reaction in which ozone is destroyed, the photolysis by ultraviolet radiation. But also reactions were discovered in which ozone is either produced or destroyed. And the simplest set of reactions which do the job we can exemplify here by the oxidation of carbon monoxide. It starts by reaction with OH. That's how most stuff is removed from the atmosphere. H atoms are formed and CO2. O2 adds to the H atom, HO2 is formed. And then depending on whether there is enough NO in the atmosphere, HO2 reacts with NO to make OH and NO2. Or in another cycle, HO2 can react with ozone to make OH and 2O2. If you go through this cycle, the NO2 which is formed here is very quickly dissociated in NO and O atoms, and the O atoms recombine with oxygen to make ozone. The net result of these reactions are that CO is oxidized with 2 oxygen molecules into CO2 and ozone. If there's too little NO in the atmosphere, then instead CO is oxidized to CO2, but ozone is consumed. And much depends on the amount of NO in the atmosphere, whether ozone is produced or destroyed. So basically, the borderline is defined by the ratio between NO and ozone, and the rate constants for various reactions enter into this. One can generally say that for NO, mixing ratios somewhere greater than 10 to the minus 11 in the atmosphere, ozone is produced, otherwise it can be destroyed. It's interesting to look at these reactions. In these photochemical reactions, we can consider carbon monoxide as a fuel. It's a low temperature combustion of carbon monoxide we are really looking at, which is sort of incinerated by the presence of photons in the atmosphere. CO is the fuel, and we see also that we have lots of catalysts being active in the production or the destruction of ozone, OH, HO2, NO, and NO2. They all act as catalysts in these reactions. Now this is the simplest set of reactions in which ozone is formed, photochemically, in sort of smog-type reactions. The next simplest case is methane oxidation, but you see already many more reactions entering into the scheme. But also methane is everywhere, like carbon monoxide, and if there's just enough NO in the atmosphere, then ozone is formed. And of course, if we go to more complex molecules like isoprene, we get about 1,000 reactions to consider, and just if there is enough NO in the atmosphere, ozone is formed, in the same way as during the oxidation of carbon monoxide. Now, NO is increasing in the atmosphere, and especially because of emissions at mid-latitudes and also in the tropics by biomass burning, about which I will speak much more a little later in the talk. With increased emissions of NO in the atmosphere, especially in industrial regions, and also increasing concentrations of, say, for instance, methane in the atmosphere, one of the fuels, and also carbon monoxide, one would expect that ozone should have gone up. And this is indeed observed. There are, for instance, records of ozone, ground level ozone, going back to the end of the last century in a suburb of Paris, Montsouris. And if these are data which have been checked by Dieter Klein and his colleagues and seem to indicate good quality measurements of ozone at that time. At that time, about 10 nanomole per mole were the average ozone concentrations which were measured. And nowadays, in environments like this, there is just much more ozone, about a factor of 2 or 3 higher. Also in the 20s and 30s, Optical measurements were performed, very often in the Alp regions in Europe. And the typical concentrations or mixing ratios which were measured at that time were of the order of, say, 20 nanomole per mole. And what is measured typically nowadays is about 2 times more, even 3 times more. And also at the station in southern Germany, Hohenpeißenberg, we see in the troposphere a substantial increase from data taken in 1968. These are the annual averages, and in 1989. So 20 years progress in ozone formation here. This increase in ozone seems to have stopped at the Hohenpeißenberg station. You see that in the later years things have leveled off. Maybe there's even a slight decrease. This may have to do with the fact that nitrogen oxides are being regulated in Europe, so that the maximum in ozone in Hohenpeißenberg may have been reached so by the end of the 80s. Of course, it's also possible that some meteorological factors have played a role in this curve. We have to further analyze that. Well, also models can be developed, and when that is done, the simplest model we developed in Mainz about 10 years ago. There are much more advanced models now being used, but I think still the principles of what is happening can be explained with a simple model we developed also initially with the help of Reginald Newell, a model of transport of chemistry in the atmosphere. We basically divide up the Earth in longitude and latitude blocks and height blocks, and then take meteorological observations, monthly mean wind speeds, and also a fudge factor, the eddy diffusion coefficients were introduced. And if we then add chemistry to the model, in this case carbon monoxide and methane chemistry, then one can, and also boundary, at the ground boundary layer values of carbon monoxide and methane, then one can start playing games. What one has to consider is that NO is put into the atmosphere by lightning. That's the same, let's say, between industrial and pre-industrial times. But for industrial times, of course, we have lots of inputs of nitrogen oxides in the industrial world, and this is then also assigned to the model. And then if one calculates how much ozone this model then produces, one gets, in the case of the pre-industrial atmosphere, and this is for the summer in July, pre-industrial atmosphere, you see a picture which, well, it's bluish almost everywhere with a few exceptions. Roughly of the order of 10, 15 parts per billion or nanomole per mole near the Earth's surface for the July case. You compare that with the present situation and you get a much more colorful figure. You see you get much enhanced ozone concentrations downwind of the main pollution sources. So an increase by roughly a factor of 2 or 3 compared to pre-industrial situation. So the models basically show the same as the observations. If one looks at the budget of ozone in the troposphere, we have a number of reactions in which ozone is formed. HO2 plus NO and CH3O2 plus NO are the reactions in the carbon monoxide methane oxidation schemes. Anytime these reactions take place, basically an ozone molecule is formed. And you see here under global, you see 2 numbers. One of these numbers expresses the amount of ozone produced in the troposphere globally in units of 10 to the 12 mole per year. And the left number is calculated for the present atmosphere, and the right number is calculated for the pre-industrial atmosphere. And you see the ozone forming reactions. You see also O singlet D plus water vapor, which is a loss reaction for ozone. There is some reaction of ozone with HO2 and partially with OH is coming in here. If you look at the chemical terms, which are shown here, you see that the chemical terms certainly for the industrial atmosphere are much larger than the flux of ozone downwards from the stratosphere, and also larger than the destruction of ozone at the ground. This clearly shows that ozone is formed and destroyed in the troposphere in amounts which are larger than the influx from the stratosphere. And interestingly, this was also true already for the pre-industrial atmosphere. Although the emissions of NO were smaller, still the chemical terms were more important than the flux from the stratosphere. So the internal budget of ozone in the troposphere is regulated by in situ chemical processes. And this is, of course, a big change from the initial belief that ozone would be a rather inert gas in the atmosphere, in the troposphere. It's, however, important to point out that these reactions which produce and destroy ozone would never start if there would not be some influx from the stratosphere into the troposphere. We have here an auto-catalytic system in which you need some flux of ozone to get it started, but then you actually produce internally much more or destroy much more than the initial flux. Also, we did some analysis of this. If you look at the ozone in the atmosphere, although the internal cycle is so important, still for the total amount of ozone in the troposphere, the stratospheric part is of large importance. In the upper part of the troposphere, most of the ozone you find there is still has an origin from the stratosphere. And that's a part which is important for climate studies. Well, I'm getting to the tropics. Before that, briefly show you this figure. This is basically the distribution of ozone, total ozone, as a function of latitude and time of the year. It's only average values. And what it shows is basically, this was, by the way, a figure which was made before the ozone hole developed, so this is a classic figure. But in general, what we see in this figure is that in the tropics there is basically always some sort of an ozone hole, a natural ozone hole. Minimum amount of total ozone is in the tropics, which has to do with the height of the tropopause, which is much higher, 18 kilometers in the tropics than at high latitudes. So most ultraviolet radiation, by far most ultraviolet radiation, comes down to the Earth's surface in the tropics. And in the tropics, you find also in general a maximum in water vapor concentration. So you would expect the highest production of OH and the highest OH concentrations in the tropics. And although we have very few measurements to confirm that, if we rely on model calculation, we see this clearly. Here is depicted the concentration of OH radicals in the troposphere as a function of latitude, southern hemisphere, northern hemisphere here, and then also height, and in units of 10 to the 6 molecules per cubic centimeter. So we have a maximum here. That means that many gases which have lifetimes, say, of the order of a few months or more, are mainly destroyed in the tropics. Examples of such gases are carbon monoxide. Here also the destruction rates depicted as a function of latitude, and methane. So this is where where the OH radical is the most active, where most of the cleaning of the atmosphere is taking place. The calculations with which these results were, these calculations can be checked. Earlier we had a wonderful chemical product which was measured by around the world, for instance by Ron Prin and his colleagues. And what is shown here is methylchloroform. Methylchloroform is a compound which basically is only produced by the chemical industry and is mainly destroyed by reaction with OH in the atmosphere. And one can compare at various stations around the world the calculated and observed mixing ratios of methylchloroform in the atmosphere. And if you look at these curves, you can hardly distinguish them. This model, as it was developed about 10 years ago, gave roughly the right results. So the OH concentration cross-section, which I showed you before, cannot be too far off from reality. This is very interesting because I repeat this now here. Basically, the curve curves I had in color indicating the breakdown of carbon monoxide by reaction with OH and methane by reaction with OH in the industrial atmosphere. That's this figure. And you can do the same game in the pre-industrial atmosphere. And you can say that this represents the destruction of methane and carbon monoxide must of course be balanced by an input into the atmosphere. So you can say that the natural sources for carbon monoxide and methane are given by this lower figure here, and of the industrial atmosphere is given here. So here we have the natural sources, here we have the sum of natural plus anthropogenic sources. The difference is the anthropogenic source. So you can use this sort of model calculations to derive a budget of ozone, of methane in the atmosphere. And what one finds then is that at present of the order of 630 million ton of methane is used in the current atmosphere. In the pre-industrial, the natural source of methane is of the order of 270, and the difference is, say, 360. So what this basically shows is that an input by human activities of methane in the atmosphere is probably somewhat larger than the natural source of methane in the atmosphere. The anthropogenic sources of methane in the atmosphere are given here. The individual amounts are still rather uncertain in many cases, but at least we know roughly what the sum of these sources should be. And you see here animals play a large role. Anaerobic fermentation is a large source for methane in the atmosphere. So ruminants and animal waste oxidation or fermentation is a large source for methane in the atmosphere. We have rice fields, biomass burning, landfills, and natural gas and oil industry leaks. It's interesting to see how important the animals are. And I don't know whether you ever have thought about it, but say a typical family of 5 people owns 1.1/4 of a cow. So somewhere in the world there are lots of cows supplying us here with cheese and meat and so on. And we have others here, so of the order of 10 chicken and just supplying us with meat. It shows what I showed you before was already an indication, strong indication how important the tropics are in all of this. To give you an idea about the fundamental step forward which was made by the discovery how important hydroxyl radicals are in cleaning the atmosphere, I give you in this view graph some so-called authoritative estimates of budget estimates of methane and carbon monoxide in the atmosphere. In 1968, there was such an analysis published, and it claimed that the methane source from natural wetlands would be of the order of 1,180 million ton of methane per year. We know now that the real number is of the order of 270. At that time, we simply was no knowledge at all available about how things were removed from the atmosphere. Anthropogenic emissions, they were rather close to each other. If you look at the CO budget, you see here number 75 in 1968, and we know now that the number here for the natural source is more like 860. And the anthropogenic source was also very strongly underestimated at that time. Good. Some of you may think that the tropics and the southern hemisphere are still clean regions of the atmosphere. There's very little industry, you might think, but there is a very important human activity already taking place in the tropics, and that is biomass burning. Whoever has been in the tropics during the dry season knows how polluted the atmosphere can be. And here we have some estimates of the amount of carbon which is burned in the tropics by various activities, having to do in many cases with rather primitive agriculture. The shifting agriculture, it is estimated that between 1,000 and 2,000 million ton of carbon is burned each year in this activity. Permanent deforestation, 500 to 1,400. Savanna fires, 400 to 2,000. Firewood burning is better known, 300 to 600. And agricultural waste burning, say 500 to 800. See, these numbers are very uncertain, but they add up to roughly about 3 to 7 times 10 to the 15 gram of carbon per year. This is a very large amount of biomass which is burnt in the tropic each year, and this is dirty burning. I mean, it's a lot of pollutants are coming into the atmosphere. So this is what is exposed to the fire. This is what actually is burned, between 2 and 5 times 10 to the 15 gram of carbon per year. And that stuff, in that burning, stuff gets into the atmosphere, and basically all the molecules we know which are contributing to photochemical smog in our part of the world also are emitted by biomass burning in the atmosphere. In mines, we have set up a little laboratory in which we can burn materials from different parts of the world, and then we look at the emissions from these materials. And we find, typically here we have the temperature of the fires, we have the flaming phase and the smoldering phase here, and together, depending on whether we are on the flaming phase or the smoldering phase of the fires, we get different kinds of pollutants in the atmosphere, like carbon dioxide, carbon monoxide, methane, and many other hydrocarbons, methyl chloride, and so on. So a rich menu of compounds are released into the atmosphere by biomass burning in the tropics. This is clearly affecting the level of pollution gases or background gases in the tropics, and not only gases but also soot and smoke particles. Here we have data from Cuiabá. This is a station in Mato Grosso in Brazil, and you see maximum concentrations of aerosol in the atmosphere coinciding with the time when biomass burning is taking place in Brazil. Now, this biomass burning produces, as I said, the same compounds, which basically also lead to photochemical smoke in our part of the world. But there's one big difference. In the tropics, this is a rural phenomenon. In our part of the world, it's mainly an urban phenomenon. So this is covering much larger areas. And we see the results of that very clearly. Again, from this station in Mato Grosso in the year 1988. in the month of September, for about half of the time, half of the days in the month of September, the ozone levels, 80 ppb of ozone was exceeded during the month of September, the time of biomass burning in Brazil. Now this is different from year to year. Some years it's just very bad, so other years it may be better. This depends on meteorological conditions. And it's not only happening in Brazil, but also in, say, Zimbabwe, in southern part of Africa. What you see here are profiles of smoke particles of carbon monoxide, carbon dioxide, and ozone, which were measured by a research team from our institute under Andy Andre. You see these maxima in concentrations, and these are the result of biomass burning, which hasn't taken place here, of course, at these altitudes at that time, but had happened somewhere else near the ground, and then the air was lifted towards higher altitudes, where then the ozone was formed. This phenomenon can not only be seen in situ, it can also be seen from space. Here we have data on the amount of carbon monoxide in the troposphere, which were measured during the wet season in the southern hemisphere and the dry season in the southern hemisphere. The blue colors mean very little CO, relatively little CO. The red colors mean lots of CO in the troposphere. And you see that in October there is more carbon monoxide in the southern hemisphere than 6 months earlier, basically the dry season in the northern hemisphere. It shows you that you cannot consider the tropics and the southern hemisphere as very clean. And this is also seen in the ozone distribution figure, which comes from Jack Fishman. In the period September to November, you see that there is this outflow, this production of ozone in the southern hemisphere, affecting large parts of the southern hemisphere, including Australia and Tasmania here. Interestingly, this model, of which I showed you some results before, simulates that. You see this tongue of relatively high ozone values extending into the southern hemisphere. So there can be a lot of ozone in the southern hemisphere, but you can also have circumstances in which you hardly find any ozone in the southern hemisphere, and that is in regions where basically you're far away from the continents, from the inputs of anthropogenic and also natural hydrocarbons and nitrogen oxides in the atmosphere. In 1993, we did measurements. This was an activity by the Center for Studies of Climate and Clouds at the center at the Scripps Institution of Oceanography, in collaboration with Dieter Kley in Germany. A cruise was made from Honiara to Solomon Islands to Christmas Island, and during this cruise balloons were launched into the atmosphere and ozone was measured. And what was often measured was ozone profiles which looked like this. Close to the tropopause, hardly any ozone, it was gone. And also in the lower troposphere, rather low concentrations of ozone in the troposphere. This was expected, but that we could end up with such low ozone values in the upper troposphere, that was new. And it was not only measured on one profile, but it was measured at on several profiles, several occasions. And this is shown in these panels here. You see very often situations in which ozone goes down to almost 0 here, and here again, etc. So this was a big surprise, and I'm not sure that we understand very well why this is happening. So if we consider the enormous importance of the hydroxyl radical in keeping the atmosphere clean, and we realize how important ozone is as a precursor for hydroxyl radicals, and how the hydroxyl radicals are mainly located in the troposphere, we must of course wonder about the ozone distribution in the troposphere, in the tropics. And we cannot say that this distribution of ozone in the tropics is a very regular distribution, because it's highly variable. We can have situations with very little ozone, or we can have situations with much more ozone whenever we are under the influence of biomass burning, for instance. So in order to understand atmospheric chemistry, we have to understand what is happening in the tropics, and we have to understand the distribution of ozone in the tropics. And unfortunately, if you look at the stations where measurements in the tropics are occasionally made, they are very few, just far too few to set up a good basis, quantitative basis for our studies. So one of the messages of my talk is that we have to improve on that situation very strongly. I would like to show you at the end a few more recent results. I showed you before this figure, which indicates the oxidation schematically of isoprene in the atmosphere. Isoprene is emitted from tropical forests in large amounts in the atmosphere, and during its oxidation, very interesting chemical things happen. And these were measured by us. In the beginning of last year, we had an expedition in Suriname. This is the former Dutch Guyana, where we, on an aircraft, measured in situ the distribution of isoprene and products which are derived from isoprene in the atmosphere with a new instrument, a proton transfer reaction mass spectrometer. And whenever we were in the boundary layer, here we have the flight routes of the plane. Whenever we were in the boundary layer, we saw isoprene, and we saw methyl vinyl ketone, and also hydroxy hydroperoxide, which derives from isoprene. So they're all there, and in fact, the model which we developed gave roughly the same results. The Lagrangian model, fed by emissions of isoprene from the forest, gave about the amounts which were measured. In fact, there was so much isoprene was emitted in the atmosphere that it titrated hydroxyl radicals to a large degree. So the average OH concentration, averaged over 24 hours, in the boundary layer over the forest, which we calculated, was only 2 × 10⁵ molecules per cubic centimeter. It's a very low amount for a tropical region. We saw other stuff in surprisingly high concentrations. One compound which is of substantial importance is, of course, carbon monoxide we saw, but also we saw acetone mixing ratios of the order of 2 nanomole per mole or even more. And acetone, it turns out, this is research of the last 5 years, is an important source for hydroxyl radicals at high altitudes. So it's definitely formed in the tropics, in the forest regions, in large amounts. And we also saw acetonitrile. This is a product of biomass burning in the tropics and elsewhere, of course. Finally, some results from a more recent campaign in the tropics. The INDOX campaign, which was conducted last February, March in the Indian Ocean region with base in the Maldives. During this experiment, which occupied some 150 scientists from all around the world, including India, during this this experiment, many measurements were made from ships, from aircraft, and also ground-based. The idea about this experiment was to see whether the pollution which is produced over the Indian continent and in general South and Southeast Asia, whether it could reach the Indian Ocean region. So we went out there, and we also went south of the ITCZ into tropical convergence zone, and you see a nice atmosphere, not too dirty, rather clean. But then, mostly we were south of the intertropical convergence zone. And there it looked like this. It was dirty over very large regions down to the ITCZ. The Indian Ocean region was highly polluted. It was polluted to such an extent that, and mostly what you see is the particles, that the optical depth of the absorption optical depth of the particles was of the order of, could be of the order of 0.4. So it's, there's a lot of, this is rather dark stuff which was out there. And the effect on the radiation balance of a substantial region over the Indian Ocean is considerable. Some estimates indicate that under these conditions, about 20% of the solar radiation which normally should reach the surface of the ocean didn't arrive there. It was either absorbed in the atmosphere or backscattered to space. So this was a rather shocking experience for us, and we were curious to find something. We were a little worried that maybe we don't find anything because it's so far away from the pollution source, but that we would find such a situation, it was a big surprise for everybody of us. So that shows that, you know, we have to start already now worrying about what is happening in the tropics and in the developing world. In the developing world, I mean, this is where most of the action will be in the future. And this is my pitch, of course. I mean, that's where much more effort should go into this research. We have to find out what is happening in the tropics. And we have so few data at the moment. So I hope that with your support and little propaganda, we can do much more of these kinds of experiments. I thank you for your attention, and hope they're still allowed to get some questions. From India, Southeast Asia, and probably also China. There's a huge population behind it, to some 2,000 million people.
That's where the basic problem lies.
Yeah. Yeah, it's wood burning. I think that's part of it, but there's also lots of dirty burning of yeah. We have to find out what actually was where it all came from. But it contained a large amount of absorbing aerosol. So it's different from sulfate aerosol.
Well, there are actually some Fox measurements in the upper tropical troposphere. How does our model agree with that?
Which measurements?
Fox.
Fox?
Yeah.
Oh, I haven't looked into that. I mean, the model, when I said the model agreed rather well with what was observed, this was for the boundary layer. You referred to the measurements in Suriname?
No, I'm talking about the Fox measurements from the ER2.
Yeah, well, I have not checked, I have not developed any model calculations for that.
Would you expect similar situations with the biomass burning in Africa and the Amazon and so, is there any evidence for a similar extension of the pollution?
I don't know. I mean, it's,
That's the question.
we have to go out there. I mean, of course, far fewer people living in these other parts of the world. I think we should follow up on this.
Paul, if you look at the tropics and you look at this large-scale perturbation to the chemical composition, to the radiant environment, are you more worried about the impact of the chemicals per se, or are you worried primarily about the coupling between chemical, dynamical, and radiant?
Yeah, I'm the latter. I am more worried about. Yes, that's the right word. But on the other hand, of course, it's also awfully interesting finding out more about this. But what does this all mean? I mean, when suddenly 20% of the solar radiation is not appearing at the Earth's surface, it must do something. Maybe not immediately. Maybe we are in the process of building up something. But yeah.
Related question. Let me say, you were doing the budgets and comparing pre-industrial quantities. What about OH? What do the models?
Well, for OH, I would not trust the models. I mean, we roughly are in the right ballpark. And I mean, we were very lucky when we got these results. And with additional chemistry we have added to the model in the meanwhile, we actually get somewhat different results, which still look quite good, but not so good as indicated here. So this, it means that in the current models, which are more advanced, there's something missing, which we did not discover before when we had much more simplified models. So it's sort of contradictory, but this is the case. So, I mean, Ron can better answer this question, what is happening to OH. There will be, you cannot say in general OH will grow or decrease by so and so many percent. There will be parts of the world where hydroxyl will increase whenever you put more NO in the atmosphere, and there are other parts of the world where it will decrease because more carbon monoxide is put into the atmosphere. And the global balance, I don't think our models are by far not good enough to derive global balance. I think we need tracers to do that and other means of doing it.
Yeah, so we published a paper a few years ago claiming that it was about 0 plus or minus 0.2 or 0.3% per year. So it's rather small. And about all we do now to modify that is increase the uncertainty. But still, it's more than zero.
Yeah.
Sometimes you learn more, you get more uncertainty, not less.
Yeah.
Well, it seems apparent that there are really two sets of problems connected with the less developed world. One is, the pollution where the people aren't, which you've just shown us. The other is the pollution where the people are in these emerging megacities, where the air is even much worse than measured out of the Indian Ocean. And, it's very difficult to get resources to study either problem. But one wonders to what extent the emissions from emerging and multiplying megacities in the less developed world, what the magnitude of that impact is on a regional and global, semi-global scale versus the story that you told us today of biomass burning.
Well,
it's not clear to me that the two impacts aren't at least a similar magnitude.
Well, the Indo-X pollution, I think, was not only biomass burning. There can also have been dirty coal burning and all of that stuff behind it. So we simply have to find out. But I mean, what will happen in the future with big city agglomerates, I mean, with 30 million people living there together, how that will change the overall chemistry of the atmosphere is a very important question. I mean, what is better, to spread out all this pollution over a large area or put it all together mainly in big cities? You create totally different, say, types of aerosol, for instance. the co-regulation in cities is so much stronger. And so what the developments of that will be, I mean, the influence of cities on, even on the global scale, is I think, a very interesting and important issue.
Well, let me ask a question on the main theme that there needs to be more studies of chemistry in the tropics. Most of the tropical countries are developing countries and they don't have a lot of resources to do this type of work. And instrumentation, certainly for things like Nobel, which is exceedingly expensive and difficult. How many Indians were in Indonesia, for example? How many Indian scientists were in Indonesia?
Quite many, quite many. I mean, if I would guess now, probably of the order of 30 to 50. So they were mainly on one of the ships, the Saga Kanya. And really quite a few of them do excellent work, so it's not a hopeless situation there. But of course, you raise a very important point. How do we get more of these people in developing countries into this game? It's high technology. And I mean, you can educate people here, but do they go home to their country then to do the research? I mean, because they stay here, because when they go home, there's nothing to do there. Their governments are not interested. But then you sit at international negotiations, and there you see mostly the scientists from the developing countries sitting in the back rows and not saying much. I mean, so they will not inform their governments. So you have this terrible vicious circle of things which in some way we have to break, but how is it's not clear to me either.
I think that situation might be a little bit better with the large cities because there are more resources in the cities, and so there's at least there are more scientists in the developing countries looking at that. But of course, that doesn't mean that more needs to be done. But as far as the rural areas, I think that at the moment I would agree with you that there's very little done. But there's also a scientific question I thought that you raised, this difference between spreading out the pollution or mitigating cities, because you have these very strong non-linearities, and you sort of alluded to one that the isoprene was titrating POH. You can also envision you have lots of nitrogen oxides that in many of these cities they begin to destroy ozone, and so all sorts of stuff.
And they're more efficiently removed than maybe if you put them all together in a smaller. Yeah. So this, I think, what is the effect of urbanization in the next century, especially, on atmospheric chemistry is an interesting question. I mean, it has its positive and negative sides. Well, I don't think at all, of course, how young kids will grow up in cities with 30 million people. That's is a totally different problem. But that's a social question which I find horrifying.
Well, let's thank our speaker again, and I invite you all to the 9th floor where we have a reception with the Ida Kingdom.